Hello everybody, this is Dr. Christopher White, and now we're moving on to the second part of sedimentary structures and fossils. So away we go. Alright, so now let's think about the final thing that we can see when we look at a layer of rock. We've already touched very briefly on the fact that a bed of rock comes in one of two types. There is a bed, which is greater than 1 centimetre, and a lamination, which is less than 1 centimetre. So the question becomes, can we glean any information from this? And the answer is kind of. So in some cases, what we can see is we do have quite thin layers, and in some cases we have quite thick layers. So as discussed, the thinnest layers, less than 1 centimetre, are laminations. Now laminations are very often deposited in very, very low energy environments where the sediment is slowly settling onto, for instance, onto the bottom of a lake. Now, those kind of laminations are commonly associated with things like mudstones, very small class size material. You can, however, get laminations associated with quite fast flowing water. So when you see a lamination, it doesn't necessarily mean that you're dealing with a low energy environment. But a lot of laminations, a lot of laminated rocks will tend to form in lower energy conditions. So it's a kind of guide. It's not really perfect, but it gives you a possible idea. Now when it comes to thick layers, well, a thick layer of rock, or should I say sedimentary rock, will typically form when we have the deposition of large quantities of sediment. So you need to have, a big thick layer of sediment will tend to form a big thick layer of sedimentary rock. Makes sense. So if we do have, big thick layers, well, that would tend to suggest that the sediment is being deposited in some kind of environment with a very high rate of sedimentary deposition. So once again, is that perfect? No. But it does give us a possible idea of the types of environments we might be looking at. Okay, so the thickness of the layer is not perfect. All right, so now we're past that. Excuse my dog sneezing in the background there. Let's think about what we have to do as geologists to actually, deal with these layers of rock. So if we just take a second and we have a look at this picture over here in the right-hand side, what you'll notice is this cliff face is just made up of dozens of layers of rock. So if I'm trying to deal with each of these layers of rock individually, it's going to be a nightmare. It's going to be very, very difficult for me to, be able to trace these layers of rock individually over very, very large distances. So what can a geologist do? Well, one of the things that we do as geologists is we try and take beds of rock that have formed in a similar environment, and we bundle them together and we produce what's referred to as a formation. So a formation essentially is several layers of rock, typically 2 or more, bundled together, and each of these layers of rock have a similar origin. So, they might be all marine, for instance. So the one thing we have to have with a formation is it has to have a defined lower contact and a defined upper contact. As long as we can see where the bottom of the formation is and the top of the formation is, perfect. That's all we need. So what can we do with these formations? Well, if we have 2 or more formations that have a similar origin, so for instance, I might have several layers which I put together and they are from a fluvial environment. So that's formation number 1. I then might have formation number 2, and those layers of rock have been deposited in a lake environment, a lacustrine environment. Now both of those are continental and both of those are freshwater environments, so what I can do is I can take those 2 formations and I can group them together to give me what's referred to as a group. So I've now taken 2 formations and I've then combined those to form a group. Then if I can find 2 or more groups that have a link, I can then combine those together to form a supergroup. And that's it. All we're doing is we're just bundling together layers of rock just to try and make, our lives a little bit easier, so we can, trace these units over large distances a bit more easily. So here's how we do it. So as you can see, here I have a sequence of 9 rocks. So at the bottom I have a marine mudstone, then I have a marine limestone, marine sandstone, desert conglomerate, desert sandstone, desert evaporite, fluvial greywacke, fluvial mudstone, lacustrine mudstone. So you can see I have 9 layers of rock. So what I'm going to do is I'm going to split these up into formations. So as you can see, these three down at the bottom, marine, 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 I can combine those together to give me formation number 1. I have a desert environment, desert environment, desert environment. I can combine those together to give me formation number 2. And I have freshwater, freshwater, and freshwater. I can combine those together to give me formation number 3. Done. So then what I can do is I can then take it a step further. You'll notice that we have continental and continental. And so I can combine those two formations together, and that would give me a group. They have a similar mode of formation. They're all 6 of these layers are of continental origin, so I can combine those together to make a group. And it really is that simple. You can see that all I did is I took, sorry, I'm just going to go back for a second, going the wrong way, is I took 9 layers and I combined it into 3 formations. All of a sudden I've slashed the number of rocks I have to deal with, and I've just made my life that little bit easier. And that's it. So now we have to have a quick think about what conformable and unconformable mean. So a conformable sequence of rocks simply says the boundary between adjacent beds or units does not represent a substantial gap in time. Or to put it another way, a succession of beds of nearly the same age that represent nearly continuous deposition. So, sorry, itchy nose. In a conformable sequence, I would expect layer A to be deposited, then layer B, then layer C, then layer D, then layer E. So a near continuous sequence, no breaks in between each layer. That's a conformable sequence. So, sorry, I should say the contacts between those layers will also be conformable because there's no loss of time between each layer. So, so layer A was deposited, 10 million years ago, layer B was deposited 9 million years ago, layer C 8 million years, and so on. So then I have an unconformable contact, and that's when 2 layers of rock touching each other, so the contact is between them, and that contact represents an interruption to sedimentation or a period of erosion. So essentially it means there's lost rock. So that would mean my layer A could date to 500 million years ago, and layer B could date to 300 million years ago. Well, that means the contact between them represents 200 million years of lost material, doesn't it? And that's what we refer to as an unconformity. And in geology, we hate unconformities because unconformities mean lost rock. It means rock that never formed, or rock that did form and was completely eroded away. Either way, the rock's not there. And if we don't have the rock, we don't have the evidence, and we don't know what was going on, because as geologists, we need the rocks. So the gap in an unconformable sequence, so where we have 2 layers of rock in contact with each other, that contact between the 2 that represents the lost time is referred to as a hiatus. So there's been a hiatus between the 2 layers. So difference between layer A, 500 million years, and layer B, 300 million years, essentially is a 200 million year hiatus. So the missing time essentially is referred to as an unconformity because the sequence is now unconformable. So if we just have a look at this sequence of rocks here, what can we see? We can see this is a near continuous sequence. It's one layer, then next layer, then next layer, then next layer, just being dumped one after another, after another, after another, after another, after another. And so this sequence here is all conformable because the contact between this cream layer here and this rusty layer above it is going to be conformable because the cream layer was deposited, then the rusty layer was deposited. There was no hiatus in between these layers. So the contact between the 2 is conformable. Now I will point out though that as you can see, something clearly happens along here to create quite a stark difference. We have these greenish sediments here, and all of a sudden we have these, browny sediments here, and that's quite a pronounced contact there. So that might actually be an unconformable contact. Not 100% sure there. I need more evidence to know. But nevertheless, this sequence here is most likely conformable. So there's no lost time between, at the contacts between these individual layers of rock. Now let's look at this as another example of an unconformable sequence. So what we can see here is we have units which have been deposited at different times. So what we can quite clearly see is at the top here we have this kind of creamy coloured rock, and then we have this kind of greyish coloured rock, and these are displaying horizontal bedding, aren't they? The bedding's going sideways, so it's going this, so from left to right. And the same on this layer down here, bedding's going left to right. However, if I come down and I drop below this layer here, all of a sudden these rocks down here, well, the bedding is going top to bottom. So there's clearly a discrepancy there, isn't there? So there's clearly some kind of feature, which is approximately where that red line is, which divides these two units. So we have this set of rocks up here, which are horizontally bedded, and this sequence down here, which are vertically bedded. Okay, so what does this tell us? Well, this is clearly an unconformity, isn't it? Because let's just think about how this will have formed. So these layers of rock here will originally have been horizontal. Remember, principle of original horizontality. The sedimentary layers will have been deposited as horizontal sheets. So what's happened? The sediment was deposited, then it was lithified, then it was tilted, then a whole load of sediment was eroded away, and then the horizontal rocks up here were deposited. So this process of lithifying, tilting and erosion of these rocks down here could have taken tens, maybe even hundreds of millions of years. And so this represents a hiatus, an unconformity in the sequence. There's lost time here. But so between these rocks here and this rock here, there could be a difference of, as I say, 10, 100 million years of lost rock. So that's our unconformity there. I hope that's relatively clear. As I say, as geologists, we don't really like unconformities because they mean we've lost stuff, and we would rather have the rock. So in terms of bedding, well, we've already looked at parallel bedding, and we know that parallel bedding forms in a variety of conditions. We've got beds, we've got laminations, some of them form in high energy environments, some of them form in low energy environments. So parallel bedding can form over a range of different environments. Now, the other two types of bedding are graded bedding, which we've already looked at as well. And graded bedding, as we know, is the result of changes in energy of the system. Typically, there'll be some kind of change in energy. The system will either get more energetic or less energetic over time. And that will essentially sort the sediment, giving you a gradational, what's the word I'm looking for? A gradational change in the sediment size over time. And you'll be able to see that in the rock record. The other type of bedding that will come up is cross bedding, and you can see it here in this picture. You can see we have these diagonal lines in the bed. Well, it doesn't look like that, doesn't look like that. So these are the result of dunes. So cross bedding is commonly associated with any environment where we can form dunes. So think deserts, think beaches, think rivers, think just off the coast underwater. So these are environments where we can get dunes, and so these are environments where we might be able to get cross-bedding forming. And so cross-bedding tells us we have a dune, and that dune is migrating due to the movement of wind or water. So this diagram here, once again, this is just really pushing home gradational bedding, because I want to make sure everyone feels that they can understand what's going on. So in the case of a gradational bedding, you can see we have a system in this case where we have one bed starting off very coarse, getting steadily finer. Then the next bed, very, very coarse, gets steadily finer. And these particular types of beds are being formed by what we refer to as turbidity currents. No, of course it would have helped if I had a picture. No, of course it didn't. Let's go back for a second. So in this instance, a turbidity current is an underwater landslide, and we've kind of touched on them briefly already. So in turbidity currents, you get a mass flow, so a landslide underwater, and that landslide comes off the continental shelf, comes flying down the continental slope. So obviously it's dropping quickly, so it's got lots of velocity, so it's moving quickly. And then all of a sudden it hits the continental rise and the gradient shallows quickly. And so it goes from moving very, very quickly to hitting a very flat surface, and all of a sudden it starts to lose velocity. And so this is what happens. Our turbidite sequence starts up here on the continental shelf, comes flying down the continental slope, and then when it hits the continental rise or the abyssal plain, all of a sudden the terrain becomes a lot flatter. It starts to lose velocity very, very quickly, and so it also starts to lose energy. And as soon as it starts to lose energy, it has to start dumping sediment. And so we can see a nice image of the types of rocks that we tend to get when we see these turbidity flows. So now the turbidity flows are made of a mixture of clay, silt and sand. And so as the turbidity flow starts to slow down, the first thing that gets dumped is, here it goes, the sandy material right here. And then slowly, as the velocity starts to get slower and slower and slower, then the silty material gets deposited. And then finally, the fine clay-sized material gets deposited. And so as you can see, as we go from the sandy layer to the silty layer, and from the silty layer to the clay layer, you cannot see a clear boundary between these layers, can you? They're all gradational. And that's purely because the energy of the system is decreasing. So it was high energy, and then slowly over time the energy is getting lower and lower and lower and lower. And so that means sediment is being constantly deposited in a steady stream. So that means you get this steady change in grain size over time, meaning that there's never any chance for a nice sharp boundary to appear. You end up with these gradational boundaries. And these gradational boundaries are simply the result of what's sometimes referred to as the settling curve. So if you remember, this is the Hultstrom diagram, and we're going to follow the red line here. And all this typically says is when you have a transporting medium, in this case water, and let's just say it starts off, up here. Okay, so it's got a velocity of, I don't know, about 75 centimeters per second. And then all of a sudden it starts to slow down. So it was at 75 centimeters per second, then it starts to lose velocity. Well, when it starts to lose velocity, first of all, it will start dumping the gravel. Then as it gets to here, it will start depositing sand. Then as it gets to here, it will start depositing silt. And then eventually, as it slows down even further, it will start depositing clay. And so as you can see, as the velocity drops, it will deposit sediment in a steady pattern. Heaviest, then lightest, then lighter, then lighter still, then lightest. So you'll get a gradational change in the type of sediment, or should I say the size of sediment being deposited. And that will result in these gradational boundaries, because this change isn't sporadic, it's constant. So once again, you can see it here. These are some more turbidite deposits from these underwater landslides. You can see here's the bottom of one of these turbidite flows, and you can see the material at the bottom is coarser, so it's going to be mostly dominated by sand. And then as you go upwards, the material steadily gets kind of darker grey in colour. That's because it's becoming more and more mud rich. And so you have sands grading into silts, and then by the time you come up to the top of the layer here, you're into muds. Sorry, you're into clays, not muds. I do apologise. So sands into silts, into clays, but once again, you cannot see those gradational boundaries because it's a steady change, not a sporadic change. Okay, so now let's think about crossbeds. Well, crossbeds are extremely useful to geologists. So we all remember how a dune works. So here's our dune. If you remember, sand comes up the stoss, hits the crest of the dune, and then comes down the lee. So sand goes up the stoss and down the lee. So what does this do? Well, as you can see, as a dune migrates along, it essentially cannibalizes itself. So a dune will take material from its rear, it will transport it up, and then it will deposit it at its front. But what you'll notice is, as the dune migrates, it leaves behind these lines here, which we refer to as crossbeds. If you were able to take a slice through a modern dune, you would see these diagonal lines in the dune. So those are the crossbeds, and they're going to be preserved in the rock that forms from this sand. So one of the things we need to know about these crossbeds, and I want you to have a look at this diagram because it shows it just about, is that crossbeds will tend to be, actually let's drop down to this diagram, it's even better. Crossbeds tend to be thinner at the bottom and thicker at the top. So one of the ways that crossbeds are useful to us is they tell us the way up. So if we have a rock and we see crossbeds that look like this, well, we know the thinnest part of the crossbed would be the bottom of the dune, and the thickest part of the crossbed would be the top of the dune. And so we know that this sequence is the correct way up. However, if we had a situation where the thickest part of the crossbed was at the bottom here, and the thinnest part of the crossbed was at the top, well, we would know that sequence had been flipped 180 degrees and the dune was the wrong way up, and that doesn't work. So we know at some point after the rock formed, it had been rotated 180 degrees, so it had been overturned. So having way up indicators is quite helpful because it tells us as geologists that yes, your rock is orientated correctly. So what else do crossbeds do? Well, you'll notice that the crossbed itself is a diagonal line. So in this case, the diagonal line is coming over here from the left and it's coming down towards the bottom right. You'll notice that they all are aligned, top left to bottom right. What this means is we can use them to tell us the direction in which the dune was travelling. So we know that the wind is blowing material, taking material from the rear of the dune and depositing it at the front of the dune. So we know that material is coming from here, coming up here and being deposited. So when we see a sequence of rocks that looks like this, okay, well, we know that this was the front of the dune. And we know that over time the dune has been migrating this way. Same with these dunes. Top left to bottom right, the dune has been migrating this way. In contrast, when we look at this layer here, we can see the dunes, the crossbeds are orientated top right to bottom left. So in this case, we know the dune is migrating this way towards the left. And so these crossbeds are very, very helpful to us because they give us an indication of the direction of flow. And so that's extremely helpful to geologists. So not only can we use crossbeds to make sure that our sequence of rocks is the correct way up, it can also tell us which way the dunes were travelling. So it tells us what the prevailing wind direction was when the dunes were forming. And, you know, that's one of those fun, interesting pieces of information that geologists love to have because under the right circumstances, that kind of information can actually be very, very useful to us. One of the things I will point out is over time, if you have a look at this sequence here, what you'll notice is you've got one layer of crossbeds over another layer of crossbeds over another layer of crossbeds. And that's simply because over time what will happen is this dune will get overtaken by another dune, and that new dune will just come right up over the top of it. And so what you're seeing here is this dune got covered over by this dune, and this dune got covered over by this dune. And so that's perfectly normal, that's what happens. So here we go. So here's a picture of the Navajo sandstone, very, very famous North American sandstone unit. And straight away you can very quickly see these diagonal lines, can't you? They're very, very obvious. You can't really miss them. Okay. Now you can also see, if you look at this sequence, there are some obvious bedding planes. So if you look here, there's a very obvious bedding plane coming across there. There's another very obvious bedding plane coming across here. Another obvious bedding plane coming across here. There's another obvious bedding plane, I think, coming across there as well. So these are the bedding planes that I could pick out. Okay, just going to show you this one here. It gets a little bit messy down here, doesn't it? So I think there's something going on there. So I'm going to give it a dashed line for a possible bedding plane. Not 100% sure. But anyway, so these are the bedding planes that I can pick out. So these each represent different dunes. So this is one dune moving across here. This is another dune. This is another dune. This is another dune, and so on. Okay, and each of these dunes is going one over the top of each other. So so this dune down here that produced these crossbeds was then taken over, or this dune then came over the top of it, and so on. Now, in terms of the crossbeds themselves, what can we see? Well, if we look, here are the directions of the crossbeds. So you can see the crossbeds are going from the top left down to the bottom right. Okay, so if we just go back, top left to bottom right. So we know the front of the dune is like this, and so we know dune's coming up. The wind is blowing the sand up the stoss and down the lee. So we know the dune is travelling to the right of the image. Okay, the crossbed is orientated top left to bottom right, so we know the dune is moving to the right. And so this is nice because as a geologist, if we can work out which way these rocks were orientated when which way the sediment was orientated when the sediment was deposited, well, that gives us the prevailing wind direction. which is always good to know. So that's the power of crossbeds. They tell us which way up the layer of rock should be, and they also tell us which way the dune was travelling that formed the crossbeds. Both very important and helpful pieces of information to have. Okay, so do you know what? We're going to stop here and we're going to do part 3. Once you've had a chance to get up, have a walk around, get some water, a cup of tea, cup of coffee, and just spend a couple of minutes just relaxing before we start the next lecture. All right, bye guys.